When physicists announced the first direct detection of gravitational waves in 2016, the discovery sent ripples through the scientific community. Gravitational waves, wrinkles in the fabric of space-time that make space itself stretch as they pass through it, were predicted by Albert Einstein over 100 years ago. Now, in a preprint article published on Arxiv, a group of researchers have their sights set on using gravitational waves to solve that other big problem in astronomy, finding alien planets. The exoplanets they think they could find would be un-Earth-like, with huge masses, orbiting close to their stars, and years that last about an hour or less. In other words, these planets would be unlikely to support life. Still, the technique is promising as another tool in our exoplanet hunting arsenal that could find planets we've so far been unable to detect at all. Even weak signals could also be detected if the sources are close enough to the Earth, José Ademir Sales de Lima, one of the authors of the paper, at the University of São Paulo, Brazil, told the Daily Beast. Lima and his colleagues decided to look at binary systems, double star systems, or a star and a planet in our own galaxy. They realized that a special class of exoplanets, the ones with ultra-short periods, could cause gravitational waves strong enough for us to see, he said. It's not just mass that affects how strong a gravitational signal an object can make. The shorter period an exoplanet has, that is, the faster it travels around its star, the stronger the gravitational waves it creates. And Lima and his colleagues think that the next generation of detectors could sense gravitational waves coming from exoplanets that travel around their star in an hour or less, as long as they're close enough to Earth. Current exoplanet finding methods have some significant blind spots. The transit method, used by NASA's Kepler mission and responsible for the majority of planet detections to date, requires a planet to orbit in front of its star. Researchers see the traveling speck as proof of an exoplanet's existence. If a star has a planet that doesn't cross in front of it from our vantage point, however, we can't see it, which means we can't prove its existence. While I suspect that detectable systems would be extremely rare, interestingly these systems might have orbital inclinations that would be much less favorable to traditional exoplanet search methods. Martin Hendry, a professor of gravitational astrophysics and cosmology at the University of Glasgow, told the Daily Beast. So far, using our normal methods, we've found a handful of planets that fit this description. They tend to be gas giants many times the mass of Jupiter and orbit close into their star, characteristics that have earned them the nickname, hot Jupiters. The gravitational waves we've seen since 2016 have been made by incredibly massive objects, typically black holes and super-dense neutron stars, as they interact. But, technically, anything with mass can make gravitational waves, most are just far too small to detect. Today's state-of-the-art gravitational wave experiments, LIGO and Virgo, consist of large ground-based detectors that use lasers to measure incredibly small changes in space. LIGO is made of two 4 km long L-shaped detectors on either side of the U.S., with one in Hanford, Washington State, and the other in Livingston, Louisiana. Virgo is similar and sits near Pisa, Italy. Gravitational waves get weaker the further away they travel from their source, so we could only detect the merging of those faraway black holes because they were so massive and started off with such a strong signal. By the time the first gravitational waves, created during a merger of two black holes 1.3 billion light-years away, reached Earth, the amount they stretched space by at our detectors was a fraction of the diameter of a proton. We're still a couple of decades out from actually measuring any planet's gravitational waves. LISA, a space-based detector being developed by NASA and ESA, is not due to launch until 2034. The possibility that some extreme exoplanetary systems could be gravitational wave sources accessible to spaceborne detectors such as LISA is an intriguing one, Hendry said, adding that gravitational waves could make a useful add-on to other search methods. Gravitational waves from exoplanets would also have a unique feature we've not yet seen from any other source. Unlike in the collision of two black holes, the signal from exoplanets would not be a one-time event. They would continually emit gravitational waves as long as the planet kept orbiting its star. This class of binary systems is very suitable for continued observation, Lima said. In other words, however long it takes us to build the detectors to measure those signals, they'll be there waiting for us.